All right, hello everyone. My name is Sacheth Sathyanarayanan, and this is Hari Ramakrishnan, and we both just graduated from Princeton University. Today we're going to talk about approximately strategy-proof tournament rules with multiple prizes. Our co-authors are Emily Dale, Jessica Fielding, and S. Matthew Weinberg, and they're all affiliated with Princeton as well. So to start, let's begin with some background on tournaments. So assume that you have a tournament on n teams, say A1 through AN, where each team plays every other team. We can represent this information using a complete directed graph on n vertices, where an edge from node AI to AJ indicates that team AI defeats team AJ. Now suppose that we'd like to rank these teams from 1 through n, depending on how good or bad they are. So in this example, the answer should be pretty intuitive. Since A4 defeats every other team, it's ranked first. Since A2 loses to every other team, it's last. And among A1 and A3, since A3 defeats A1, it gets a better ranking. And so the optimal ranking should be A4, A3, A1, and A2. Note that here the answer is intuitive because we were able to come up with a ranking where each team defeats every other team that it's ranked better than. However, this may not always be possible. For example, consider this tournament. So note that no team defeats every other team, and no team loses to every other team. So it's impossible to come up with a ranking where each team defeats every other team that it's ranked better than. Furthermore, there's a cycle in this graph. So A1 defeats A2, A2 defeats A3, and A3 defeats A1. So it's not immediately obvious what the relative ordering of these three teams alone should be. Well, so how do we rank teams in these more general tournaments? We use tournament ranking rules. But before I get to that, let me talk about tournament rules. So current literature defines a tournament rule as a mapping from a tournament to a distribution over teams. And the idea here is that a tournament rule tries to find the winner of a tournament. So for example, it could claim that the winner is A4 with some probability or A1 with some probability. And we extend the notion of tournament rules to tournament ranking rules, which are mappings from tournaments to a distribution over rankings from 1 to n. So for example, a tournament ranking rule could claim that the ranking is one of these three with some attached probability. For a tournament ranking rule to make sense, we'd like that it satisfies certain measures of fairness. And one such measure of fairness is called Condorcet consistence. And it's defined as follows. So if there exists a team that defeats every other team, and such a team is called a Condorcet winner, that team must be ranked first with probability 1. So for example here, team A4 defeats every other team, so it's a Condorcet winner. And for R to be a Condorcet consistent tournament ranking rule, it must rank A4 as first with probability 1. Another notion I'd like to introduce is that of a prize vector. A prize vector is a non-increasing n-dimensional vector where the semantic meaning is that the ith component is the prize awarded to the team ranked ith. And we normalize these prize vectors by assuming that each component lies between 0 and 1. Now, since a tournament ranking rule claims a certain ranking with some attached probability, it also claims that each team gets a certain prize with some attached probability. Thus, we can define the notion of the expected prize of a team under some tournament ranking rule. So a property of tournament rules that we're interested in is how resistant they are to manipulation. And we're interested in a very specific kind of manipulation. So assume that you have a set S of colluding teams that decide to fix the result of their match so as to increase the total expected prize of S. And we define the total expected prize of S as being the sum of the expected prizes of each of the teams with an S. Okay, let me provide some motivation. Assume that you have a corporate sponsor, say Nike, that sponsors a set S of teams. And further assume that Nike takes a certain percentage of the winnings of each of the teams that it sponsors. So now Nike has an incentive to maximize the total expected winnings of the teams that it sponsors since that increases its revenue. And let's say it decides to do that by encouraging 2 or more teams within S to collude or fix the result of their match so as to increase the total expected prize. That's the kind of manipulation that we're interested in. So for example here, you can think of S as being the set A1 and A2, the teams that Nike sponsors. And in the first picture, if A1 defeats A2, we see that the total expected price for the set A1, A2, which is the sum of the expected prices for A1 and A2, is 0.9. But if A2 defeats A1, it goes up to 1.2. So now A1 and A2 have an incentive to fix the result of their match so that A2 defeats A1, so as to increase the total expected prize of that set. Also, such tournaments that differ only in the result of the matches among two or more teams within S are said to be S-adjacent. So these two tournaments are identical except for the result of the match between A1 and A2, and so they're S-adjacent tournaments. All right, I'm going to introduce a little more notation. So first we have alpha PKR. So here P refers to the prize vector that's under question. So remember, these prize vectors are normalized so that each component lies between 0 and 1. K is the maximum size of the set of colluding teams. So in this example, we had 2 teams colluding, so K would be 2. And R is the tournament ranking rule that we're studying. And alpha PKR is the maximum prize money that a set of at most K teams can gain in expectation by manipulating T to an S-adjacent T prime. So in this example, a set of 2 teams was able to increase their total expected prize by 0.3. So this alpha KPR would be at least 0.3. And we're also interested in results over a set of prize vectors, or all possible prize vectors. So when we replace P by the set P, we mean the supremum alpha KPR over all possible prize vectors P within that set. Okay, I'll talk a little bit about related work. So far, all related work on the manipulability of tournament rules has only considered the winner of a tournament. They haven't been focused with ranking the teams, but rather just finding a winner. So the question there is, can a set of teams collude so as to increase the probability that one of them would be the winner? And within our notation, we can think of that as just considering the prize vector P equals 1 followed by a bunch of zeros. And previous authors have come up with 3 different tournament rules: randomized single elimination bracket, randomized king of the hill, and randomized death match, such that alpha sub 2, so a set of 2 teams on that prize vector, is a third. And they've also shown that this is the best possible results that you can get on any Condorcet consistent tournament rule. And there's also other results on collusion among teams of size greater than 2, but we don't really know how good or tight they are. So the focus of our work, as you've probably guessed, is on tournament ranking rules, where we try to rank each of the teams and not just find the winner. And in this regard, what we've done is we've proposed a new tournament ranking rule called the nested randomized king of the hill that Hari will get to in just a second. And we've proven 2 main results on this tournament ranking rule. So the first is, for any set of 2 teams that decide to collude, they can't increase their expected prize by more than a third. So it's the same result as we saw with previous authors, except we've proven this over all possible prize vectors, not just 1 followed by a bunch of zeros. And our second result is that on a specific prize vector called the Boulder prize vector, which we define as a linear increase from 0 to 1, so 0, 1/3, 2/3, 1, or 0, 1/4, 2/4, 3/4, 1. So on that prize vector, no set of K teams can get anything in expectation by colluding. So it's a non-manipulability result. All right, so we'll have Hari now talk about the tournament rule.
Thanks, Sacheth. So now I'll introduce this tournament ranking rule itself, called nested randomized king of the hill. Some of the technical details of how it proceeds are on the screen, but to give you an overview, basically what we do is we pick one of the teams at random from our set of n teams. We call that team the pivot. And then we take every team that is defeated by the pivot, rank them below the pivot, take every team that beats the pivot and rank them above the pivot, and then we simply recurse on both of these individual sets. So this is pretty similar to quicksort, where you pick a pivot when you're sorting an array, and you put every element below it on one side, every element above it on another side, and recurse on both sides. Except now our comparator, instead of being the actual value of some numbers, is who wins particular matches. And so this also isn't necessarily transitive, as we've seen in Sacheth's example when there were cycles. So for example, we'll look at one iteration of this algorithm. We can take a look at this particular instance of the tournament, and we randomly pick a node. Let's say we pick A3 to be the pivot. We see that A2 and A4 both beat A3, so we're going to rank them above A3. And we see that A1 loses to A3, so A1's going to be ranked below A3. This now fixes A3's rank, and then we recurse on both sets. On the bottom, there's really nothing to do because it's just A1. But on the top, we have that A4 beats A2, so we give A4 rank 1 and A2 rank 2. So this gives us our final ranking of A4, A2, A3, and A1. And of course, this is dependent on the order that we pick the pivots. So this is one possible outcome. That's randomized king of the hill. So now getting to our main results about this tournament rule itself. So we've shown that alpha 2 of NRKOTH for any prize vector is 1/3. So this means that no pair of teams can gain more than 1/3 in expectation by manipulating their match. And again, the units of this 1/3 are because our prize vector is normalized to be between 0 and 1. So we have results previously showing that for the prize vector of 1 followed by a bunch of zeros, any Condorcet consistent tournament rule has this value to be at least 1/3. So now we've extended this bound to all prize vectors, making this the best possible type of this result for all Condorcet consistent tournament ranking rules. The second result that we've shown is that for the Boulder prize vector, which Sacheth introduced, which is basically a linear increase where the first place team gets a prize of 1, the last place team gets a prize of 0, and then everything in between is filled in, we've showed that no set of teams of any size can gain anything in expectation by colluding. So this is a non-manipulability result. We've shown that there's absolutely nothing that can be gained when teams choose to collude over a uniform prize vector. So we'll walk you through a brief sketch of how we showed this second result. So we started by defining a notion of consistency under expectation. We call a tournament ranking rule consistent under expectation if it satisfies this property. For any team A in the tournament, team A's expected rank under this ranking rule must be equal to 1 plus the number of teams it loses to. So essentially, if a team beats everyone else, we'd expect that it gets rank 1. If it only loses to 3 teams, we'd expect that it gets 4th place. We see that this is actually a stronger notion than Condorcet consistence. So any tournament ranking rule that is consistent under expectation also satisfies Condorcet consistency, making this a stronger notion. And we managed to show that NRKOTH, or nested randomized king of the hill, is in fact consistent under expectation. To give kind of a high-level overview of how we proved this, we show this over induction on the number of teams in the tournament, and we managed to condition over the selection of the first pivot. So we say that we fix a team U, we're trying to find the rank of team U, and we say that in the first round, either U is the pivot, or a team that U beats is the pivot, or a team that U loses to is the pivot, and we can kind of work through these cases and work out all the algebra, and we get this desired result. So some more remarks on consistency under expectation. We can kind of directly apply this notion to get our non-manipulability result for the Boulder prize vector. Basically, since the set of teams isn't going to gain any new wins through collusion, they're also not going to gain any expected rank, and so they're not going to gain any expected prize. For prize vectors that are close enough to this uniform prize vector, we call them epsilon adjacent prize vectors. We can also get another bound of 2k epsilon, where again, k is the size of the set of teams that are colluding, and epsilon is how close each element is to that of the uniform prize vector. So earlier I mentioned that nested randomized king of the hill kind of has this similarity to quicksort. But when we looked at other sorting-based ranking rules, we found they didn't actually have this property. So we took a quick look at a merge sort-based rule and a bubble sort-based rule, and neither of them had this property of consistency under expectation. And neither did a single elimination bracket-based tournament ranking rule. So we found that this is definitely something special about this particular rule. Basically, to conclude, we've extended the work from a study of tournament rules to that of study of tournament ranking rules, and we've introduced a tournament ranking rule and showed manipulability and non-manipulability results on that. We specifically looked at the class of all prize vectors as well as the uniform prize vector. So some future work that we'd be interested in is considering other classes of prize vectors and kind of seeing how our bounds are going to change just based off the type of these prize vectors. Thanks so much for listening to both of us. We're super happy to be here, and we're happy to take any questions.
Great, we have some time for some questions.
I have a couple of questions. Can you hear me?
Yeah.
Good. So first of all, this is very cool. I wanted to ask, could you give some intuition on this zero manipulation for the Boulder rule and uniform price vectors? And then do you have any lower bounds for manipulations of size 3 or more?
So For the border prize vector itself, that was for any size. And kind of the intuition is basically that because the prize vector is linearly increasing in the rank of the team, it's a direct consequence of the fact that your expected rank is the expected number of teams you can beat.
I see, I see.
For teams of size greater than 3, the analysis gets like much more complicated. So we haven't found any new results for sets of size greater than 2 for other prize vectors.
I see. Okay, thank you.
Thank you.
Yeah, my question is, you said that it's like impossible for a group of 2 to gain more than one third. Is this tight?
Yes, it's tight over all Condorcet consistent. Oh, yeah. So the question was, is there a bound of 1/3 for sets of size 2 colluding? Is it tight? Correct? And the answer is yes. It's tight over all Condorcet consistent tournament ranking rules. And we can come up with examples where they can actually collude to gain a third.
Just to like clarify, the 1/3 lower bound is very easy. It's just like 3 teams that beat each other cyclically.
Yes, exactly.
There's this related problem called feedback arc sets, where you want to order the vertices of your tournament and to minimize the edges which go backwards. And I think there's a paper which shows that your algorithm is an approximation of the optimal solution for this, which is an NP output.
Right, I'm familiar with that paper. I think Noga alone proved that it was NP hard. I'm not sure how good an approximation this is, but I think that would be interesting to think about. And also, to repeat it for the audience, sure, the remark was there's a related problem called the feedback arc problem, that you're trying to minimize the number of times, at least in this setting, a lower ranked team defeats a higher ranked team, and that this tournament ranking rule could be an approximation to that problem. But yeah, thank you for that. All right, if there's no other questions, thank you guys so much.